Welcome to an in-depth analysis of the Klon pedal. This is a Klon pedal. This one, the KTR, was designed by Bill Finnegan, the creator of the Klon, and it's manufactured in a contract manufacturing factory. Then I have this one, which was built here by me, but a company in Malaysia makes this, Tone. And so this is what the original Klon looks like. It's still the same 3 knobs, gain, treble, output. And you can get miniature ones, sugar drive. You can get standard pedal size ones. You can also get more boutique ones, such as the Archer Klon here. And then you can also get kits. Here's a kit, Silver Pony. And then you can also get them from Stewie Mac. There's this Ghost Drive, all the same circuit essentially. And then you can get Chinese ones as well off the website called Wish, or the Wish pedals. This is one here, got another one over here. And what we're going to do in this analysis is actually butcher up one of these cheap Klons. It costs about $25 to be able to perform the in-depth analysis, because we're going to have to desolder some resistors, remove the chip, put some switches in, and change obviously the golden diodes that there's a million YouTubes about to see how they perform. And we're going to totally destroy it. So I think it's this one. In about 5 hours will look completely different. The first port of call for a Klon analysis is the Electro Smash website, and go to the Klon analysis. We have a picture of the original Klon, circuit diagram, which we'll look at in a second, description of what's inside it. The power supply we're not going to cover, but the power supply is a high headroom power supply. I've covered it in my booster videos. So it's a 24 volt power supply, which is done by this MAX1044 voltage converter. I also use this in when I want to create a negative voltage for all germanium PMP pedals as well, so it's pretty good. Because there's a frequency response plots, how the input buffer works, how the clipping works, and we're going to cover all that in this video. The key thing and the center of this video is to understand the clipping stage and the 2 feed-forward networks that go around the clipping stage as well. But I found, though, through this analysis, that this summing op amp has an integrator function here through C13, and that really affects the tone and takes a lot of the fizz out. So we'll discuss that in the video as well. So let's zoom back to the schematic. So here's our schematic. So first of all, we have input buffer. It's a TL. The unit has 2 TL072 op amps, pretty standard guitar pedal amplifiers. And this is op amp 1, these 2 guys, and this is op amp 2, these 2 guys. First is a buffer. It's a very simple buffer, 0.1 coupling cap on the input, so it's going to attenuate frequencies probably less than 20 hertz. And you'll see once we go around this circuit here, one of the upper feed forward, we'll see that the roll off is about 15. It happens at about 15 hertz. The buffer can either be switched to go through the circuit or to go directly out. So when this pedal is not being used, i.e. switched off at the foot switch, this buffer is still in place, so it's permanently buffered. The next thing we do is we go into this gain stage here. And the thing about the op amp gain stage is that through the center here, it has an op amp. It has these diodes here, what they call the magic diodes that define the tone. And then it has 2 feed forward stages. So feed forward around here at the top, and feed forward around the bottom. So I'll call those the feed forward top and bottoms in the video. And then this is the op amp gain and clipping stage here in the center. So I'll explain how it all works and how the diodes contribute to the clip and how the op amp also contributes to the clip. But we have a lot of filtering as well here. This is optimized around mid-frequency boost, so we can get a good distortion, but it's peaked in the mids, and then the fizz, you'll find out, is taken out with this summing op amp. And this is quite an innovative idea to use an integrator with a feedback resistor as well. So that changes the square wave essentially that's coming out of here into a triangle wave, or more subtly put, it looks like a shark fin. And then we've got the tone control here, and the tone control is controlled by this pot here, and that allows us to adjust, or this thing really, its main function is to brighten the signal up. It's called the treble. I think that accurately describes it, and you'll see in the video that it really enhances higher frequencies, frequencies above, say, 800 hertz. Then with the output here and the output pot, foot switch, output jack, and of course down here at the bottom we have the power supply. We've got the three controls: output, treble, and gain. So this pot here and this pot here is this gain, and we're going to go in depth how this gain works, because it's actually two pots connected to a single spindle. And then treble is here in this feedback loop around the second op amp, and then output is here. So let's dig in. Let's figure out how this thing works and get to a really in-depth understanding of the circuit and the circuit dynamics. It's going to look like this. We'll have added a couple of switches here. One switch would be to bypass the upper feed forward loop. The other switch here is to bypass the integrating capacitor on the third stage, the summing stage. Then we've got a switch buried down here where we're switching the diodes from the shipping diodes that the pedal came with to LEDs to give a little more headroom and see how it performs. So it's completely butchered, and it's probably repairable. But again, it's only a $25 Klon. If anybody would like this, just contact me. So I have the scope probe on the upper feed forward loop. I'm currently sending in a signal of 30 hertz, and we're looking at the blue trace. So if we take that down to 20 hertz, amplitude looks about the same. Reduce it to 19, 18, 17, and we can see now that the blue signal compared to the green signal is reducing. So this is a high pass filter that rolls off at about somewhere between 12 to 17 hertz. So why don't we take that back up now to 100 hertz, just the time base, and then crank that up to 1 kilohertz. Same amplitude, it's tracking. Take it up to 2 kilohertz, and the whole thing rolls off at 2 kilohertz. So it's a high pass filter, and given that the whole thing rolls off, i.e. the whole thing, all the traces got smaller once we got to 2 kilohertz, that's the frequency response of the whole system. So the upper feedback loop is a high pass filter that attenuates all signals less than 17 hertz. So in terms of your guitar, which is about low E string, which is about 80 hertz, it's going to pass the whole signal. So how does that affect the rest of the pedal? So let's take a look at that. So this is a scope probe here, and I've got it on that resistor on the feed forward loop. So what I'm going to do now is actually lift that resistor out and see how that feed forward loop affects the signal. So let's desolder this thing. I've set the signal generator frequency to 100 Hertz, and we've got a sine wave, and that is purely, well, actually it's a combination of the upper feed forward signal path and the lower feed forward signal path. So first of all, let's disengage the upper feed forward path, and the signal reduces. And let's re-engage, and the signal increases. So what we're getting is a clean signal path. On the upper one, it's constant because there's no pot, but on the lower feed forward, as we increase the gain, we also at the same time reduce the amount of signal going on the lower feed forward. And this signal that's increasing now, this is the gain stage with the diodes. And as you can see now, we've hit diode clipping here, so the signal's slightly clipped. And again, if I disengage the upper feed forward, small signal reduction, and the waveform rounds off a little, I engage it again and we get a signal increase. So what this tells me is that the upper feed forward passes bass or lower frequencies constantly, doesn't add distortion, it's nice and clean, while the lower feed forward is a function, how much signal that's passed is a function of the gain pot. So this is all gain stage, and then as we go down, we're just going to see the contribution of the lower feed forward and the upper feed forward together. So now let's increase the frequency to a kilohertz. Just the time base. So at a kilohertz, if I switch this thing in or remove the upper feed forward, marginal. Can't see anything. It's back on the upper feed forward now. The upper feed forward's on, and then I adjust the gain. Of course, now the filters are optimized for the higher frequency. So the gain stage, I should say, with the diodes is more optimized for mids. So we can see the signal increases a lot more, and then we can hit well-defined clipping. This is the output. And at this point, I think we're clipping also the summing amp, and maybe I think we're clipping the summing amp, or the summing amp's clipping here as well. And then the tone stack amp, I can't comment on that right now, but it's either clipping or both those amps have a lot of headroom, but the summing amp has a lot of gain, so it can go into clipping earlier. Okay, so what have we learned? We've learned that the upper feed forward passes bass. It's got a roll off at around 15 Hertz, and the gain stage and the lower feed forward have a roll off starting more around 130 Hertz, but are really optimized for the mid frequencies. So what we get is a combination of, when we're in gain, so that is 100% now going through the gain stage and 0 going through the lower feed forward. So we get a contribution on the bass end of the clean feed forward on the top. And then as we roll down, so this is just the lower feed forward now and not the gain, we get a contribution on the low end. So the low end's increased, it's equalized, it's increased a little due to the upper feed forward. But in respect to the mids here that we see, it's a marginal change. I'll just switch it in and out again. So that's really interesting behavior, and part of the behavior that gives the Klon a unique sound. So why don't we have a look now at the clipping diode behavior? Now I'm going to put channel 2 on of the scope, and I've got this connected to pin 7 of the op amp which is the output of the second stage or the clipping stage. So this is the signal that feeds the diodes. So if we scroll down or reduce the signal, now the output of the op amp is less than the clipping voltage of the diodes. And as we increase, now we can see we're exceeding the clipping voltage of the diodes on the purple. And as we keep going, we continue to increase again until the op amp reaches the rails and that starts to clip. So everything squares off a lot at this point, and we're overdriving a lot of things. If you look, overdriving a lot of stuff, if you look at the green, which is the output, you can see that the shape of that seriously increases as the op amp increases, driving those diodes really hard to at this point where the diodes are just switching on and then switching off. And when you're down here, it's more subtle and rounded, more subtle and more rounded. And then here, the diodes are switching on and off. And we're overdriving the summing stage and maybe the tone stack stage as well, because we have this green curve here. You see that curve, which means something is being, some frequency components being heavily attenuated there. So that's how the whole center section works with the feed forward and the diodes. One last thing, because I've got LEDs on this. Let's try and switch in the LEDs. Okay, LEDs are in. So now, when I adjust the gain, everything takes a lot longer to clip, because instead of clipping at 1.4 or 1.3 volts, we're now clipping at 4 volts. Then you see the green. Actually, at this point, I think we're at 10 or 11 o'clock. That's completely off. So that's about 10 or 11 o'clock with LEDs. That is a super high headroom at 1 kilohertz clean boost. So let's test it a little. Increase the frequency. Oh yeah. Oh, it goes down in frequency. Obviously this is optimized, and it's probably because I got the tone set in the middle. But it's very clean, although attenuated. Peaks at a kilohertz in this specific setting. But with the LED diodes, we do get a very good clean boost. So that's another technique. If you're trying in search of the perfect clean, mid-frequency boosted pedal, swapping the diodes to LEDs gives you a really nice clean headroom. And then once you get to midday, the output now is clipping. So I suspect that's a summing amp clipping, and it just continues to drive it hard. So now you can see that the purple's clipped, so that's the diodes clipping, and then the blue is the op amp hitting the rails and clipping, and that's a pretty dirty distortion at that point. Now let's look at the summing amplifier, where those 3 signals are going to be summed. Technically it's 4, because there's 2 signals coming from the lower feed forward. There's 2 filter networks there. Let's just call it 3. So the upper feed forward, the gain stage and clipping diodes, and the lower feed forward. And the feed forward is essentially all high pass filters. The high pass, the lower feed forward, is emphasized to boost signals above 500 to a kilohertz, and the upper feed forward is optimized to boost really low frequency signals, such as your lower E string on the guitar. So what we've got here on the scope now is the output of the summing amplifier. There's quite a lot of gain in this. And so if we just do this, just turn up the gain slightly. So the purple trace is on the clipping diodes. So that gives you an idea of the gain. So we go from about half a graticule to 4 graticules, and we're at 2 volts peak to peak. So a volt peak to peak to 2, 4, 6, 8 volts peak to peak. So in dBs, that's quite a substantial gain. And then the purple's are clipping diodes. So there we go. Now the diodes are clipped. And you see that clipping effect kind of turns the output into a shark fin until finally the gain is all the way at full blast, or 100% going through the clipping and the upper feed. So there's no signal going down the lower feed forward, and the signal contribution of the upper feed forward is marginal now. And so we got a hard clip going, and that clip is predominantly caused by the op-amp clipping and just driving the diodes really hard, and we get this shark fin effect. And then we roll it back again, so the diodes aren't clipping anymore, and we go into this lovely clean boost area. So if we change to the LEDs, we get and turn the gain up, or divert the signal from the lower feed forward and put more of the signal into the gain stage, and turn up the gain at the same time. We just start to clip here, and then you can see we get the same effect as we begin to hard clip. It turns into a shark fin, and roll it back, but just on a bigger scale. So, and you know, when we're here, you know, it's 2 volts per division, and we got 10 divisions. So that's a lot of voltage. That's 20 volts. Yeah, that would, and that's fine. And then we begin to clip out 20 volts because the power supply is 24 volts. So what causes that shark fin effect to happen? I believe it's due to the capacitor that he has in the feedback. So it's an 820 picofarad capacitor. And so what I'd probably like to do is disconnect that and check that if it's that is having this contribution here, so when we clip and send much more higher frequency components through it, that we get this shark fin effect. So let's do that. We have the capacitor removed now, and one of our probes, the purple one, is on the clipping diodes, and the blue is on the output of the amplifier. So if we go back, there's no clipping, and that is a summation of all 3 of our signals represented by the blue, and then we clip a little. Now that signal, the blue signal, represents the summation of the upper forward feedback, the lower forward feedback, and the clipping signal itself. And then the more we clip the signal, the more of an emphasis, or the more the clip signal begins to dominate the signal as we go all the way through to max clipping, where the op-amp now is actually the dominant clipping contributor, and we get this very sharp edge. So on the oscilloscope, when we see a sharp edge like this and a sharp edge like that, that means there's a lot of high frequency components there that make up that edge, and that would create a very fizzy signal. So the idea of that capacitor is, on these high frequency parts, put enough negative feedback through the system, or through feedback, enough negative feedback to attenuate these edges, and that's how we end up with the shark fin. So that was a pretty good idea. So we're going to solder the capacitor back in place to get it back to its original working condition, and then we're going to examine the final part, the tone stack. Okay, last section. Let's see how the tone control works. So I've got the signal generator actually connected directly to the tone control circuit, which is the last half of the second op amp. You know, there's a certain amount of coloring that's gone on in the feed forward networks and the gain network, plus there's capacitors, you know, on the front end as well, giving a high pass filter. So I thought the best way to do this, to get an accurate analysis, is to connect directly to the tone stack and then measure the signal, and that's the green signal on the scope that you can see on the output of the pedal. So currently I've got the tone set to 0, and I've got a 200 kilohertz tone in the signal, 200 kilohertz, 2 kilohertz tone. And if I wind that up, I think it stays about the same, maybe a little bit of roll off, but we're at 4 kilohertz at that point. So let's get back down. All right, so we're less than 2 kilohertz now, 900 amps. So it definitely, so that's 1 kilohertz, and go to 900, and you can see the amplitude increases. So this, we're at 100 hertz now. So this, when the tone knob is set to 0, we're getting an amplitude boost. Yeah, that looks like it. We're getting an amplitude boost of frequencies less than about 1.5 kilohertz. There it goes. 1.5 kilohertz. It seems to be flat as well once you get into the gain zone or out of the gain zone, which is indicative of the way the amplifier is designed. So now I'm going to take the tone knob and move it halfway. So I'm at 500 hertz now. Let's take that down a little bit. We're at 500 hertz and we're at halfway. So let's take it down. That's 100 hertz. A little bit of gain increase, but not a lot. 1 kilohertz, 2. I'm going back down again. It's marginally increasing. We're at 2.2 kilohertz now with the tone set halfway, and we're cranking up past 4 kilohertz. So the interesting thing is, with the tone set halfway, there is some effect on the tone. The signal does get larger once you get higher than a kilohertz, and tends to shrink once you get less than a kilohertz, but not by that much. So there's a sweet spot in the middle here, and depending where you set the tone control, that the output tone circuit probably has no or a marginal effect on the output, and that's very hard to actually determine without instrumentation, and it would be specific to every single pedal. One thing that we talked about in the introduction is that the tolerances on the potentiometers are quite high. So every pot is different across every Klon circuit. So if I did all these measurements, you know, accurately and trace them out on one Klon, then they'd be all different on another Klon. So somewhere in the middle, I'm going to say, you can set the gain pot, not the gain pot, the tone pot, so it's marginal or no contribution to the overall tone. So now I'm going to move the tone pot to max after adjust our scale here. And we're at 1.3 kilohertz. So let's crank that up. Yeah, look at it go. So when it's in max, it's passing a lot of high frequencies. And it's still passing a lot of high frequencies. We're at 5 kilohertz. So it continues to grow. So let's wind it back and see. So we're in roll off. So we've just passed 3 kilohertz coming down. That's 1 kilohertz, very attenuated now. 200 hertz and down to 100 hertz. So super attenuated compared to, let me enter in 5 kilohertz. Look at that, it's just filled the whole screen. It's filled the whole screen with tone. So yeah, that's good. That, you know, that sounds like it's going to be quite noisy. A lot of high frequencies is always not a good thing. But don't forget, on the stage before, the summing amplifier with the capacitor around the outside, the integrator function, we're not passing that many high frequencies. The high-end fizz is suppressed. So I think, you know, overall we know this is a good design, and a lot of thought has gone into how the pedal works. So that's how the tone control works. So somewhere in the middle, I think you could say marginal contribution to the overall tone. When it's turned down, we're emphasizing lower frequencies opposed to higher frequencies. And when it's turned up, once you get over 1 kilohertz or 1.5 kilohertz, we see amplification of those frequencies. All right, so that's the end of the circuit analysis. Why don't we plug the guitar in and just go through those tones as well, just to verify what it sounds like. Now I've got the tone set to minimum. I've got the gain pot set to about 9 o'clock just in, so I'm not clipping the diodes, and if I do, it'll be a transient that does that. And I'm on the neck pickup, tone set to 0. So let's now set the tone to halfway, still on the neck pickup. Much more treble. I'm glad it's labeled the treble pot. So now let's put it on full. You can hear a lot more high frequency noise coming through now. Much more sparkly. In fact, ear-piercingly sparkly. I've got P90 pickups. Again, I did the whole thing on the neck pickup. And that's it. That was, we're now 5 hours later. And we've completed a very, very in-depth technical overview of the Klon pedal. I hope you enjoyed it. Please like and subscribe. And I look forward to talking to you in the next video. Thanks a lot.